Okay, so this problem is maybe not quite as obvious what the applications of it would be, but it's still an interesting example. You've got 100 centimeters of string or wire or whatever you want to think about. You can cut this string once in any place you like, and then you can make a square out of one piece and a circle out of the other piece. Or you can choose not to cut it at all and just make a square, or not to cut it at all and just make a circle. And the question is, of all of these things, what should you do to get the greatest total area once you do this? You might be able to guess this answer. This is the only other one other than the first one, I think, where you could reasonably guess the answer. So what's our goal? Maximize the area. So our formula area, the area of a square is length times width. So in this case, s times s, or s squared. And the area of a circle is pi r squared. So as usual, I hope you hope that you have by now seen the pattern of all of these. We write our formula, it's our function, it's a function of more than one variable, so there's some other information in the problem that we can use to solve for one of those variables and then plug it back into this function. What else do we know here? The 100. So we also know that 100 is the total perimeter of the square plus the circle. So the perimeter of the square is what? S plus s plus s plus s, 4s. The perimeter of the circle is 2 pi r. Look at that. That's interesting. The derivative of the area of the circle is the perimeter of the circle. The derivative of the area of the square, though, is not quite the area. The derivative of the area of the square is not quite the perimeter of the square. You can think about why it's different for a square than for a circle. You can also might like to think about what happens when you take the derivative of the volume of a sphere. Do you get the surface area of a sphere? And if you take the derivative of the volume of a cube, do you get the surface area of a cube? It's an interesting thing to try to figure out. Okay, so we've got this, and we would like to solve for one of these variables. It's not apparent which one is easier to solve for, so I'm going to solve for s. So I'm going to get 100 minus 2 pi r over 4 equals s. So that's the same as saying s is 25 minus pi over 2 r. Neither one is particularly nice to solve for in this case. So we've got our s here, and we're going to plug, now we have a entirely as a function of r. So a of r is s squared, so this whole thing squared, 25 minus pi over 2 r quantity squared, plus the pi r squared that we already had. So what do we want to do with this now that we've got our formula down to one variable? We want to take the derivative. So here you could multiply this out if you wanted, or just take the derivative as it is. I'm going to take the derivative as it is. That means we're going to use the chain rule. We've got something squared. The 2 comes out front. The inside stays the same. And then we take the derivative of the inside. The derivative of 25 is 0. Derivative of negative pi over 2, r, is negative pi over 2. And then the derivative of pi r squared is 2 pi r. So some things cancel here. These 2's cancel. And I think we can factor a pi out of this term and a pi out of that term. So if we factor out a pi, from this we've still got the 25 minus pi over 2r. And from this, when we factored out a pi, we've still got a negative 1. And from this, when we factor out a pi, we've got a 2r. There are many, many different ways to solve this equation. If you're choosing something different, that's fine. Just make sure we get the same thing at the end. What kind of equation is this, by the way? It looks terrible, but it's actually just a what? It's just a linear equation, right? We just have r to the first power. So we're solving a linear equation here. Okay, so let's do it. So pi, if I multiply this negative 1 in here, these two switch signs, right? So it's negative 25 plus pi over 2r plus the 2r that we already had back there. We should stop to see, can this ever be undefined? It was linear, so no, it can never be undefined. We're just going to try to set this equal to 0. So if we're setting this equal to 0, could pi be 0? Pi can't be 0. So this whole thing must be 0. So let's clean that up a little bit. This is negative 25. I've got two r's here. I wish I only had one, right? So plus r times pi over 2 plus 2. So this thing here is what we must be setting equal to 0. So if you set that equal to 0, so that means that 25 must equal this, r times pi over 2 plus 2. So r must be 25 over pi over 2 plus 2. Sometimes it's not so nice looking to have a fraction inside of a fraction. So what could I multiply by on the top and the bottom? Multiply by 2. So I get 50 over pi plus 4 equals my r. All right, what are we supposed to check now? Is this the what? We are looking for a max. So is this the max? We do our number line just like we've done on all the other problems. 50 over pi plus 4. And I'm checking the max of area. So I'd like to pick a number on the left of this. So say I pick 0. And if I plug 0 into my derivative here, this might be the easiest way to plug it in. If I plug 0 into this, these become 0. I get pi times a negative. I get a negative. So area is decreasing out there. Is that what we were hoping for? That is not what we were hoping for. And if you pick a number out here, you get a positive. So this is actually the way to get the minimum combined area. It would say, make the radius of your circle this, and use all the rest to get the minimum combined area. But that's not what we wanted. We wanted the maximum combined area. So that's the first time of the optimization problems we've been doing that our critical point did not turn out to be what we wanted. So we need to think back now to last time. What do we do? Where else can a global maximum or minimum be if it's not at the local max or minimum? It can be at an endpoint, right? So we have to figure out what are the endpoints, because it's saying the graph is somehow coming, the graph of the area function is somehow coming down like this and then up like this. And we're trying to figure out, is this point higher or is this point higher? Now the problem that we did in week 7, we actually were given what the endpoints were. Here we're not. It's up to us to figure out what they are. So in other words, it's up to us to figure out what is the smallest possible value of r and the biggest possible value of r. That's what the endpoints are going to be. So the smallest possible value of r should be when we don't use any r, right? So the smallest r, what are the endpoints, is the question that we're trying to answer. The smallest possible r is when you don't use any circle at all. So that's 1 is r equals 0. And the other endpoint is when you use everything for the circle, right? This represents doing just the square, not cutting it at all and using everything for the square. The other one is when you don't cut it at all and use everything for the circle. So this is all square. And then the next one is all circle. So if it's all circle, that means you're using 100, all of it, in the circle. So in other words, r is 50 over pi. That's all circle. Remember, this is one that I said you might be able to guess the answer. So have you guessed it correctly? If you haven't guessed yet, what does your intuition say? Which will give you a bigger area, all square or all circle? See if you can guess right. So what are we supposed to do now? Now we're supposed to try to plug these into the actual original function. So we're supposed to figure out what a of 0 is and what a of 50 over pi is. Right? That's how we find a global max or a min when it's not at our critical point. We plug into the original function. We're trying to compare the y values of the original graph. So a of 0 is 25 minus pi over 2 times 0 squared plus pi times 0 squared. This means there's no circle. You're using everything for the square. So the square is 25 by 25. So you get 625 units of area if you use everything for the square. This is when we use all circle. So this is 25 minus pi over 2 times 50 over pi squared. But this will all cancel out. This will end up becoming 0 because this represents making no square at all, plus pi r squared. So when we square the 50, we get 2,500. On the bottom, I get a pi squared, and on the top, I had a pi. So this is 2,500 over pi. We're supposed to compare which of these numbers is bigger, 625 or 2,500 over pi. Now, of course, you can get out your calculator right now and put 2,500 over pi into it and see if you get something more or less than 625. But it's actually not too bad to do without a calculator because 625 happens to be 2,500 over what number? Over 4. So if we do all square, we get 2,500 over 4 units of area. All circle, we get 2,500 over pi units of area. Which of those is bigger? Well, we know pi is less than 4. So the fractions have the same numerator. This is a smaller denominator. So this is the bigger fraction. And thus, that's the answer. To get the maximum area, what should we do? We use all of the string, all 100 centimeters, for the circle. And so you might have guessed the answer to that, as I said, because somehow a circle is a more efficient use of perimeter than a square. If the question had been a square and an equilateral triangle, what do you think the way to get the optimal, the greatest area would be? You can make a square and an equilateral triangle or any combination of the two. In that case, it would be all square because a square is more optimal use of a perimeter than a triangle. If you had, say, an octagon and a pentagon, what would you do? The octagon is more like the circle, so you would use everything for the octagon. A circle is, you can think of a circle as being a polygon with infinitely many sides to it. And I had a friend who once gave a question on an exam, a very hard exam, where he actually did sort of a family of curves one for this, where one of your shapes was an n-gon, meaning a regular polygon with n sides, and the other was an m-gon, a regular polygon with m sides. And the question there was actually to find the minimum combined area. And so then you had to go through the thing like we did up above, except that you didn't know it was a square and a circle. One thing had m sides, the other thing had n sides. You're welcome to go and try that on your own if you have some spare time.